and welcome to Retail Fueling 101. My name is Ed Kammerer, and I'm the Director of Marketing and Global Product Strategy for OPW Retail Fueling. And today we're going to talk about all the magic at a gas station. Pretty much everything you want to know about retail fueling, but we're afraid to ask. So if you think about it, most people pull up at a gas station once or twice a week. They swipe their credit card, put the nozzle in their vehicle, fill their car, the nozzle shuts off, and they drive off, and they don't really think about what just happened. Well, at OPW, that's actually all we think about. It's our job to make sure that we design and manufacture products that keep both people safe and the environment. If you think about it, we've got people out there that are actually handling and fueling with a Class 1B flammable and combustible fluid. So that liquid can be pretty dangerous if it's not handled properly. And the other piece is the keeping our planet, our environment safe. Gasoline's nasty stuff, so we want to try and keep it out of the ground and keep gasoline vapors out of the air. And that's pretty much what we do here at OPW. So throughout this video, we'll talk about all the different components, how they come together, why we do the things we do. Many of the things that we do or you see at a gas station is actually driven by regulations. And there's a couple different bodies in play here that come up with the requirements for the equipment and the regulations and the testing criteria, things like that. So we'll talk about a couple of those. The big one obviously is the EPA, Environmental Protection Agency. They kind of control, keeping our planet safe, keeping Earth safe, keeping things out of the ground that shouldn't be there, and making sure that people aren't harmed or our planet's not harmed by these harmful chemicals that could end up in the ground. Another one of those agencies is the NFPA, the National Fire and Protection Agency. They're kind of in charge of making sure things don't blow up or catch fire. So we'll talk about some of the things that they're involved with and the equipment and how we keep or make the equipment safe for people to refuel with that combustible and flammable fluid. And then finally is the Air Resource Board, the ARB. Each state is kind of tasked with controlling their air pollution and making sure that air is clean. And so each state has their own agency, and probably one of the most famous or one that a lot of the industry follows from the manufacturing standpoint, and other states kind of follow behind when it comes to regulations, is California. So you hear me say CARB or California Air Resource Board quite a bit throughout the video as well. So before we go any further though, again, this is going to be a high-level overview of the equipment and how a gas station works. So if you're a crusty old petroleum veteran and you already know the difference between an emergency valve, an overfill valve, or an anti-siphon valve, you may want to back out of this video now and check out some of our other videos, our 201s on OPW University on YouTube or at opwglobal.com, and you can get into some more detail where we talk specifically about products in a little bit more detail. But if you're brand new to the industry, maybe one of our distributors, or you're a regulator or an inspector, someone new to the petroleum industry, this is probably a great video for you because we're going to give an overview of how everything comes together. So actually the way a gas station works, it's pretty simple. It's basic fluid mechanics or fluid dynamics. We're really just transferring liquid or fluid from point A to point B. But in our case, that liquid is gasoline or diesel or some other type of fuel. So we'll go over what happens in between there, how we keep that liquid out of the ground, how we keep those vapors out of the air, and the individual pieces of components that fall into place as we transfer that fuel from point A to point B or from the tank to your vehicle. So when we first did this video about 8 years ago, it ended up being about an hour long. There's a lot of information to cover. But what we wanted to do this time is kind of break it up into segments or modules. So you can watch one segment and then maybe come back, pick up on the second one, and then pick up on the third one. Or of course, you can always just watch all 3 or 4 consecutively if you'd like. So there's really 4 components or 4 things that have to happen at a gas station and able to get our liquid or our fuel from point A to point B. Number one, we have to have a way of storing that fuel in some type of vessel or container. That way it's there when we're ready to use it. Number 2, we have to have a way of refilling that vessel or that tank. Number 3, we have to have a way of transporting that fuel from point A to point B or from the tank to our vehicle. And then finally, we have to have a way of measuring that fuel as it leaves the system and goes into our vehicle. So that's kind of what we'll focus on and how we'll break down our segments throughout the video. So let's talk about that first component, and this will be the first segment of our Retail 101 video. We're going to talk about how we store that fuel in the ground. So in the case of retail fueling sites or gas stations, The way we store that fuel is in what we call an underground storage tank, or a UST. So I'm warning you right now, throughout this video, we use a lot, the petroleum industry uses a lot of three-letter acronyms. So I'll try and explain them as we go on. So the first one will be UST, underground storage tank. And that's where we put the fuel on the, at the gas station. And there's a couple reasons why we put that fuel in an underground tank versus an above ground tank. First of all, these tanks are pretty large. They can hold anywhere from 8,000 to 30,000 gallons of fuel. So you can imagine a tank that large sitting up above ground is going to take up a lot of room or a lot of space at our convenience store. Plus, it's a lot safer if we just put them underneath the ground. They're less likely to be hit by other vehicles or crazy things that can happen above ground. So, really from the very beginning, we put these things underground. And they're typically buried anywhere from 3 feet to 6 feet under the ground. Over top of them will be what we call a tank pad, it's usually about 6 inches of concrete. And then on top of that tank, we fill it with what's referred to as backfill, some type of rounded gravel or pea gravel, or sometimes they use sand depending on where the tank goes. But we put these things in the ground, like I said, to keep them out of the way and kind of keep them safe. The early days, these tanks were made of steel. Again, large steel tanks that they buried in the ground. But if you think about it, the problem with steel, underground environment, a lot of moisture, groundwater, a lot of different things happen. So steel tanks were susceptible to corrosion, not only outside, but inside as well. With gasoline and water, water is actually heavier than gasoline. So many times throughout the system, if there's leaks or something happens, a lot of times these tanks will end up getting water in them. And what happens is the water goes directly to the bottom of the tank, so the tank can also rust from the inside or the bottom out as well as the outside. So originally the industry started to try and protect the tanks from corroding by what they called cathodic protection. They put these they're called sacrificial anodes around the tank system, and these anodes were down in the ground. And the idea was, through chemistry and electricity, the anodes that would cause corrosion on the tank would actually be attracted to the sacrificial anodes and rust those out versus the tank. They were a little cumbersome, required a lot of inspection and testing. So what the industry decided to do was kind of move from steel, or at least better ways of protecting the steel. So a lot of the steel tanks, what you see now is a steel tank will be wrapped or lined with some type of composite material, whether it's a fiberglass material or some type of other composite material, to try and protect the steel tank from corrosion, like I said, both outside and inside. But now, primarily, a lot of the underground storage tanks that we see going in the ground are made completely of fiberglass. Fiberglass is a good material. It's easy to form in big shapes, and it's completely resistant to corrosion and all the nasty things that happen under the ground, and also some of the crazy things that happen inside the tank with different additives and fuel types. So fiberglass, whether the entire tank is made of fiberglass or whether the steel tank is lined or coated with fiberglass, it's kind of the norm for today as these things go in the ground. Originally, these tanks were just a single wall, but the EPA, and there's another three-letter acronym that I use quite a bit, EPA, again, their job is to protect our environment. So a lot of these tanks, when they started leaking, the EPA said, okay, we need to try and correct this. So EPA started requiring double wall tanks, and we'll use double wall a lot in this video because it applies to a lot of the other components, but we'll first start with the tank. So what I mean by double wall, it's basically a tank inside of a tank, or a tank outside of a tank. So the idea is you have a primary container, and if that container fails, you have a backup, or what we call secondary containment. And that makes these tanks a little bit safer on the ground, less likely to leak. Now, another thing that we'll talk about in these double wall systems, like I said, you've got a primary tank and a secondary tank. There's a space in between those two tanks that's called an interstitial space. So we'll refer to that as well. The interstitial space allows us to kind of monitor what's happening between the two tanks, and it's an easy way to detect if one of them or both of them are leaking. So our tanks, double wall, usually either made of fiberglass or coated or lined with some type of fiberglass. We bury those things in the ground. Typically you'll have 3 tanks is pretty common. We'll have one for each type of fuel. Usually one tank will be for the regular fuel, one tank will be for the premium fuel, and actually they kind of blend those at the dispenser to make the mid-grade, but we'll talk about that later. And then maybe our third tank is diesel or some other type of fluid or fuel that the site wants to sell at their station. So we bury these things below ground. So As they're sitting under the ground, the next thing we'll talk about is these tanks need to breathe. Gasoline, actually, the thing that's fascinating about gasoline is a liquid that really, really wants to be a gas. That's why it's really a good fuel in internal combustion engines and burns very efficiently in those types of engines, is because it wants to be that vapor or that gas to ignite and refuel, and it's what, like I said, moves our internal combustion engines. So what happens is, as gasoline sits in that tank, it begins to vaporize and become vapor. But as that happens, it actually builds up pressure. I think a great example of this is if you think about the gas can that's in your garage. If you got a plastic gas can, and if it sits over a long period of time, you see it kind of starts to bulge a little bit or stick out a little bit. And then when you open it, you'll kind of hear it release pressure. Well, what that is, that's the gas sitting in your gas can, and over time, it starts to vaporize or evaporate and build up pressure, and that pressure needs to be released. Well, the same thing happens with our underground storage tanks. As they sit, gasoline vaporizes and builds up pressure. So if those tanks were tight and we allowed them to build up pressure, that could create a problem. The tank could crack or explode, heaven forbid, and we'd have a nasty situation. Again, everything we're trying to do here is to keep gasoline out of the ground. So how these tanks breathe, we do it through a vent line. So there'll be a vent that's attached to the top of the tank and goes to what we call a pressure vacuum vent. Our vent line comes from the tank, and then it transitions underground, and then this is what we refer to as a vent stack. It's usually a 2-inch piece of galvanized steel. It starts underground from the vent pipe. Vent pipe's usually made of fiberglass or some type of flexible pipe material, and it comes up above ground, and the pressure vacuum vent is actually what allows that tank to breathe or maintain equilibrium or try and get as close to barometric pressure as possible. And so the other thing that happens, if you think about an underground tank, is not only as the fuel sits there, it builds up pressure, but as people fill their vehicle, we're pulling that liquid out of the tank. So think of a milk jug. As liquid goes out, if nothing replaces that liquid, the thing will start to implode or cave in. So that's the other thing we want to try and prevent, is as liquid's pulled out, that tank builds up a negative pressure or a vacuum. So we need to keep that whole tank in equilibrium. And that's the job of this little guy here called the pressure vacuum vent. It sits on top of the vent stack, and its job is to maintain the pressure within that tank. So the EPA, along with some of the Air Resource Board, specifically CARB, they kind of set the standard of how much pressure we want to keep in that tank before it opens. Obviously, you don't want it open all the time because the gasoline vapors would just be going into the air and causing pollution. And you don't want to have too much of a negative pressure. So these things need to open at various pressures or negative pressures or vacuums. So they kind of set what those ranges are. And the way we measure these, it's in really small increments of pressure. You probably know what a PSI is, a pounds per square inch. Well, the way we measure pressure in a tank is with inches of water column. And just kind of give you an idea of how small of an increment this is, there's approximately 27 inches of water column in 1 PSI. So we're talking really small amounts of pressure or vacuum. So this vent is actually set anywhere between 2.5 and 6 inches of water column. So when the tank reaches over 2.5 inches of water column, it opens. And the way these work, the pressure, it's simply just a weight with a seal at the bottom. So that weight is designed to be tight, everything under 2.5 or 3 inches of water column. But as soon as we get greater than that, the weight would lift up or crack, and that tank would kind of come back into equilibrium or come back into pressure. So on the opposite end of that, as we take fuel out of the tank, we build that vacuum or that negative pressure, and this vent is actually set at between 6 and 10 inches of water column, which would be basically a negative pressure or a vacuum. And the way that's regulated is on our weight, there's also what we call a poppet that's spring-loaded, and as we reach that vacuum level, the poppet will be drawn down, and the tank again would be kind of brought back to equilibrium. There's a screen in there that just keeps debris and then obviously a cap because we want to try and keep water out of the tank. So when that liquid becomes a gas or a vapor, those vapors are comprised of hydrocarbons. And actually the term that we use, another three-letter acronym for you, is a VOC, a volatile organic compound. And as those gasoline vapors get into our atmosphere, that's kind of what creates a lot of pollution and smog. So the EPA and the Air Resource Board, these guys, they monitor air quality, basically county by county in each state, and make sure that there's limited numbers of these VOCs in the air and the atmosphere to try and eliminate or knock down as much pollution and smog as possible. So again, we want to try and keep those air vapor or those gasoline vapors out of the air, and the pressure vacuum vent is one of the ways that we do this. So if you pull up to a gas station, it's pretty easy to identify and see these. Like I said, they're 2-inch pieces of pipe that come up from the ground. There's usually one per tank, so you'll see 3, 4, or 5 lined up. They typically put these vent stacks on the edge of the property, or they may be on top of the canopy or on top of the store. But if you notice, they're always, kind of raised up above. There's actually a requirement that this pressure vacuum vent on top of the vent stack needs to be at least 12 feet in the air. And the reason that we do that is gasoline vapors are actually heavier than air. So if we had that vent releasing some of these vapors as it opens to bring the tank into equilibrium, if it was low to the ground, the vapors could collect around the ground, and if someone walked by with a lit cigarette or something, we could have a bad situation, an explosion, and so we want to try and prevent that. So by raising these pressure vacuum vents 12 feet up in the air, it gives a chance, the gasoline vapors, as they come out of the vent, the air around them, kind of is moving, and it allows the vapors to dissipate so they don't become, hazardous or combustible or flammable. So we talked about storage tanks that hold gasoline. Let's kind of switch over to diesel, because diesel is really a different animal than gasoline. Where gasoline is a liquid that wants to be a vapor, diesel really doesn't care. Diesel doesn't want to be a vapor. That's why diesel engines are completely different. They're based on compression versus a spark plug that actually ignites a vapor. And so if diesel, like if you spill gasoline on the ground, you probably notice it doesn't stick around very much, it evaporates. But if you spill diesel on the ground, it doesn't go anywhere, it just continues to be an oily mess. So because diesel doesn't vaporize and build up pressure, our underground storage tank, our diesel vent, is actually just an open vent. There's no need for a weight or a spring for a pressure vacuum vent. We just have an open vent to atmosphere. There's usually a cap on it, again, to keep rain from getting in that vent stack. But if you go to a gas station, look at your vent stack, you'll probably see two different type of vents. The pressure vacuum vent usually look something like this, and then the open diesel vent will just be maybe an aluminum thing with a cap on it. And we'll talk about the difference between diesel and gas as we move through some of the rest of the things with our underground tank. So behind me are the vent stacks. We talked about they're usually at the edge of the property, the very edge of the property line. You can see that they're more than 12 feet up in the air, and again, that's to disperse the vapors. This particular vent stack, you see there's two pressure vacuum vents up there. That would be for the unleaded and the premium tank, and then the other vents are actually open vents for the diesel tank. Remember, the diesel doesn't vaporize like gasoline, so a diesel can have just an open vent. It's not required to have a pressure vacuum vent. So these are what our vent stacks look like, again, at the edge of the property line and at least 12 foot above grade. So that's how we store our fuel. Big tanks underground, a vent line, and some type of pressure vacuum vent or an open vent is kind of what keeps everything in equilibrium and keeps our tanks either from exploding or imploding or cracking or causing a mess. So we have these big tanks underground, anywhere from 8,000 to 30,000 gallons of capacity. But how do we get fuel into those tanks? Obviously, as people fill up, those tanks empty out, so we've got a way of get fuel back into those tanks. So the way we do that, you probably already know this, you've seen the big transport trucks. They're usually big stainless steel things you see going down the road, and they come from a terminal, and this is how we get our fuel actually to the site and into the tank. The way that we get fuel in there, all these tanks have a series of openings on top of them when they're manufactured. And these openings, it's traditionally a 4-inch opening. It's a female NPT flange or fitting that's built in the tank. We actually call it a bung. It's called a bung fitting or a bung opening. And on these 4-inch fittings, what we have is, it's called a riser pipe. and it's a 4-inch, usually steel pipe, Schedule 40 or galvanized pipe that goes from the tank to the surface or to our grade. We refer to the surface here as grade or grade level for our tank pad. So how we access the tank in many different ways is in these 4-inch riser pipes that come up from the top of the tank and it gives us access at grade. So let's talk about how the fuel gets from the transport truck to the underground tank. So the way this works is the transport truck hooks up a hose. We call it a drop hose. It's usually a 4-inch hose that it'll hook up to the truck itself. It comes through a hose, and then this valve here is called a drop elbow. It's basically just like it's almost like a big nozzle, if you will, but it's 4 inches, and it connects to what we call an adapter. And it's usually made of brass or bronze. The reason is that drop elbow is a different type of metal, and so you want bronze or brass to prevent it from sparking. Obviously, sparks at a gas station are not good, especially when we're dealing with large volumes of gasoline or vapors. So there's an adapter. We call this a tight fill or a tight adapter, and that drop elbow will clamp on there. Once he's clamped on the tight adapter, he'll go back to his truck, open a big valve at the truck, and now the fuel flows from the tanker truck down into the tank. And the way that happens is there's no pumps really involved. It's just pure gravity. Think about it, the tanker truck is sitting up high, the tank's below ground. So as he opens up that valve, gravity just drains the fuel that he has in that tank down into the underground storage tank, or our UST. Most of those tankers are usually compartmentalized, so part of it will carry gasoline, one part maybe different grades of gasoline, and one part is diesel. So if you see these tanker trucks, you may see several of these openings or these valves on the side of the truck, and those are all different types of fuel as they drop from the tank into the underground storage tank. When originally when these tanks were filled, our 4-inch riser pipe came up from the top of the tank. We had our adapter threaded on top of the tank. Our adapter has a cap on it what's not being used. Again, we want to keep those vapors inside the underground storage tank and don't let them come up. So there's a tight cap that goes on our adapter. But this basically just came up from the ground, and it was right at grade level, usually under some type of in a box, or just a pure manhole cover to keep the backfill away so you could get your drop elbow on. So what would happen is every time the driver came, made a hookup, made his drop, every time he pulled off, there's always a little bit of residual fuel left either in that drop elbow or a little bit in the hose, and it would drip down and basically just end up into our backfill. And in the early 80s, a lot of the EPA regulations that we talked about actually came to be in the early to mid 80s as the EPA really got involved, noticing that there's a lot of pollution, groundwater pollution, things going on, and a lot of it was coming from retail gas stations that had been in the ground for years and were kind of operating in this manner. So as they began to study, where the fuel was coming from around gas stations that have been in service for a while, what they found out was most of the fuel wasn't coming from leaking tanks or leaking components as part of the system. Where most of the fuel was coming from was at these drops or during these drops. So every time the tank was filled, there'd be some residual fuel that ended up, and over time, as it got in the backfill, it turned out to be quite a substantial amount of fuel that caused problems. So in 1988, the EPA said, okay, hold on. We got to find a way of keeping that fuel out of the ground every time a transport driver makes a drop. So what the industry came up with is what's called a spill bucket. It's called a spill bucket, a spill container, an over spill container. So it's got a couple different names. But really what it is, it's just a bucket that sits on top of our 4-inch riser. It houses our adapter. And now, when the transport driver makes a fuel or a fuel drop, he'll hook his elbow up in here, and any residual fuel is now captured in this spill bucket. These things are typically 5 gallons or up to 15 gallons. They can be made of composite material. They can be made of stainless steel. So there's different ways of manufacturing them. But now, any fuel that we have left over in the hose, or if he should overfill this thing, is collected in this spill bucket and doesn't end up in the ground. Just like our tanks, These spill buckets can also be double walled. There's actually many states that require a double wall spill container. Again, we would have a primary bucket and a secondary bucket with an interstitial space. A little float here allows us to monitor the liquid level to see if there's possibly a leak on one of those. And so we have double wall spill containers, but still a lot of them are also single wall that go on the ground. So that is our means of what we call overspill protection. So I'll go back to our other graphic here. So let's talk about our underground storage tank again and think about a couple things that happen. So if we have fuel in our tank, and if we add fuel, if we're filling that tank, there's an area of our tank. Actually, I'll switch to another graphic here. It's a little bit easier to see on this two-dimensional drawing. But you can see we have our underground storage tank, and part of that tank is liquid or fuel. And everything above that is the empty space. And again, that gas has been evaporating or vaporizing. So what we have in that empty space above is gasoline vapor. It's actually a name for that empty space between the liquid level and the top of the tank. It's what we're referred to as the ullage of the tank, or really how much capacity is left in that tank. So what happens is the ullage of our tank is comprised of these gasoline vapors. So our pressure vacuum vent is doing a good job of kind of keeping those vapors in there unless the tank reaches a point where it needs to go back to equilibrium and the pressure vacuum vent opens. But primarily those vapors just sit there. So if you think about this, as a drop happens, that liquid level is rising up, right? So those gasoline vapors are being displaced. They have to go somewhere. If we kept the whole system tight, again, we'd have the tank would crack, or we'd build up too much pressure in the system. So those gasoline vapors have to go somewhere. So again, going back to the early days of gas stations, really what would happen when a driver would fill the tank up, all those vapors that were in the ullage of the tank would basically just travel through the vent pipe and go right out the vent stack. So as he filled up, all those vapors just coming out at a pretty high rate into the atmosphere. And again, kind of goes back to the late 70s, early 80s, as the EPA is trying to get a handle on pollution, and they started looking around saying, okay, wow, we got a lot of VOCs that are coming from these fuel stations, and really every time a tank is filled, it's emitting all these hydrocarbon vapors. So the industry said, okay, or the EPA told the industry, all right, petroleum industry, you got to figure out a way of controlling this. So what we came up with is what's referred to as stage 1 or phase 1 vapor recovery. So now what happens is, as fuel is dropped into the tank, before the driver makes that drop, he has another hose on his truck. It's referred to as a vapor recovery hose. It's usually orange. They try and separate the two, and usually a bit smaller diameter. A vapor recovery hose is usually 3-inch. So what he does now is he'll hook up that vapor recovery hose also to his tanker truck and his drop hose or his fill hose. And because if you think about what happens, the underground storage tank is filling up with liquid and it's displacing vapors. Well, really the opposite is happening in that tanker truck. You have a tanker truck where liquid level is now dropping, so you need to replace the liquid with air or gasoline vapors in our case. So now he hooks up two hoses, the drop hose and the vapor recovery hose. So what happens is, as the fuel level rises, the vapor now, instead of going out our vent stack, comes up through our vapor recovery hose and actually goes back into the tank. So he's collecting those vapors back in the tank. So everything kind of stays in balance. We prevent the vapors from getting in the air. And it actually turns out to be a good thing, because the vapors go back in the tanker truck. And what they do is the tanker truck will take those vapors back to the terminal, and they have a pretty cool way of turning those things back to gasoline. They chill it and compress it and condense it, and they are actually able to take that vapor and turn it back into some liquid so they can resell it at the terminal. So better than going up and causing pollution, it's actually turned back into a liquid fill. So this whole process of collecting vapors from the tank during a drop is what we call stage 1 vapor recovery. So what I'm showing here is what we refer to as a 2-point fill. 1 point we're dropping, and the second point, we're actually collecting the vapor. So we have two different hoses. In some cases, especially in older tanks when we started going over to or requiring stage 1 vapor recovery, they may not have had enough openings on their tank to have a 2-point. So they will use what's called a single point fill. And the way that works is there's one riser pipe and one hose, but the hose is actually what we call coaxial. Coaxial meaning kind of a hose within a hose. So on a single point, the fuel drops down the center, and the vapors come up on the outside of our riser or our drop tube, and then they go back through the hose. Again, the hose has in the center is fuel, and the outside is vapor. So they collect them through there through a coaxial drop tube. Actually, I have a graphic here that shows what that coaxial drop tube looks like. You'll see the two hoses that kind of come up from there. But primarily, you see, especially on new construction, everything they try and do is 2-point. You see here, this is actually what's referred to as a multi-port, where we actually have our fill and our vapor recovery is in one large chamber under one large lid, and our two spill buckets are side by side here under this one chamber. So we got our fill and our vapor in one, and this is referred to as a multi-port. These are actually pretty common in California, New York City. You'll see a lot of states utilize these, and the reason they do these is because you actually can have access to the top of this tank and your risers because you have this big chamber here. So that's what's referred to as a multi-port. But on the other stations, what you'll see, or the other type of fueling sites, is this would be a little bit more typical. This would be our 2-point, where we have a spill bucket here and our vapor recovery spill bucket here, and the driver would hook up. Now at the stage 1 vapor recovery point, that can either be a spill container, or many times it's just a manhole to kind of house that vapor recovery adapter. Because if you think about it, we're not filling or dropping product in there, so if everything goes the way it's supposed to, you shouldn't have any fuel coming out of that riser pipe where our vapor and our vent pipe is. So that could also be just a standard manhole. So stage 1 vapor recovery is a way for us to collect the vapors and keep them from going out into the tank or into the atmosphere, and that's how we get our product from the tanker truck down into our tank to be used and sold somewhere else down the line as you pull up and fill your car up. So we talked about how we get our fuel from the transport truck and into our underground storage tank. But let's think about this. What happens if that driver's not paying attention? He opens up his valve, he starts filling the tank, doesn't pay attention, and that tank fills up. Or, say we have 4,000 gallons of ullage left in our tank, and he's got 5,000 gallons in his tanker truck and just starts filling and not paying attention and overfilling the tank. Well, believe it or not, it actually happened quite often in the 60s and 70s. So again, getting back to the 80s, not only were the 80s the best decade for music, the best genre for music, but the 80s were kind of, when the EPA really started realizing, okay, we can have to start regulating and doing some things and adding equipment at these fuel stations to try and protect our environment. So again, going back to the 80s, a lot of these were specifically written in 1988, and stations had 10 years to comply, or everything new starting from that had to have these types of equipment. So we talked about a spill bucket. So at that exact same time, the EPA said, okay, we have a way of protecting from overspill, but we also need a way to protect from overfill. And so transport truck drivers, were aware when the tank reached capacity or was about to reach capacity and didn't overfill. You think about what happens if that tank, where the fuel goes, it usually would run up the vent pipe and end up spewing out the vent stack, or if there were other openings somewhere in the tank, fuel would come out and then end up in the ground. So to prevent this, the EPA said, okay, not only do we have to have overspill, but we have to have some type of overfill. And there's really two ways we can accomplish that. The first way is with an overfill alarm. So typically what that would entail is there's a float that would be down in the tank, and as the tanker truck emptied and filled the UST, the float would come up, and the magic number is about 95%. We want to be aware of the tank before it overfills about 95%. So when that float would hit 95% capacity of the tank, an alarm would signal. The driver would know, okay, I'm at 95%. I got to shut off my valve from the truck, and then I still got a little bit of room left in that tank, so I can drain what's left in my drop hose down into the tank. So that's one way of overfill prevention, is with an overfill alarm. The second way, and probably the more popular way, and I'll tell you why that is with an overfill prevention valve. And what the overfill prevention valve is, it's a valve that's down in the tank, usually has some type of float mechanism, and what happens is, actually I happen to have one. What happens is, as the fuel rises in the tank, again, we set the float at about 95% of capacity, and actually how that's accomplished is when the tank is installed, a contractor, these will be assembled in the field, he knows the distance from the tank from grade, how deep it's buried, and then the diameter of the tank. So he'll adjust there's a tube that goes up above here and a tube that goes below here, and he'll adjust that to make sure that this float sits in the tank right about 95%. So what happens is, as the fuel comes up, this float will rise up, and you'll see this poppet here, and basically that poppet ends up in a stream of fuel coming down. Typical drops about 400 gallons a minute. So fuel's coming down, fills up, this goes in the flow, slams shut, and as it slams shut, it kind of shakes the hose a little bit or shakes the truck. So again, alerting the driver, okay, I'm at 95%. Let me shut off the fuel coming out of my tank and going to my hose. I can drain my hose down in the tank, and I know that the tank is full. So the advantage of an overfill valve versus an overfill alarm is an overfill alarm requires the driver to take action. An overfill valve, you think about it, that thing floats up. Even if the driver doesn't eventually, shut the flow of product off, this float will reach a point where no more fuel can enter the tank. So even if the driver doesn't take action, the overfill valve will prevent the tank from being overfilled. And the way that these things work, again, so there'll be a tube, our poppet stays inside here outside the flow of product, and this tube would come all the way up and go inside of our spill container, and then the bottom tube, there'll be a bottom tube down here, goes all the way to the bottom of the tank, and that's what's referred to as a drop tube. And the reason we do that is we want that drop tube to go all the way down and be below the level of the liquid. If we didn't have a drop tube, if we just dropped gasoline in the tank and it kind of came right to the top of the tank and just splashed down, that splashing would cause excessive vapors. Again, would cause excess pressure buildup in our tank. So when we do these fills, we make sure that the drop tube is always below the liquid of the tank. So those things usually sit about 6 inches from the bottom of the tank. So now as the product comes down and fills, it's below the surface, so the level inside the tank just slowly rises up, and we don't have a bunch of turbulence, and it kind of minimizes the pressure buildup in the tank and the vaporization during a fill. So, two things that we're trying to prevent: overspill and overfill. An overspill bucket and an overfill valve. So let's talk about some of the other openings on top of this tank. Like I said, these are all usually a series of 4-inch bung openings that they put on the top of the tank as they make it. So we'll go back to our kind of our two-dimensional graphic here that shows some of these other openings. So if you look at this one, what's down in this opening is what's referred to as a tank probe. And a tank probe goes back and it's electronically connected to, guess what? Another 3-letter acronym, an ATG, an automatic tank gauge. And what that does is that probe goes down into the tank. It's called a magnestrictive probe. It's a metal probe, and then there's a float. And as that float rises with the level of the fuel, the magnet senses the position on the rod, sends a signal back into the store where there's a whole automatic tank gauge, a series of software, and a computer that kind of monitors and measures the level of that fuel. If you want to know more about this, you can check out some of our ATG 201 videos that we have through our sister company, OPW Fuel Management Systems, and they'll tell you all you want to know about tank gauges and how those things work. But they're pretty cool because not only do they allow the store operator to see the level of his fuel, a couple things, he wants to make sure he has enough fuel to sell to his customers, or he also needs to know when he reaches a certain level, hey, I need to order fuel and have my transport truck driver come and refill my tank. So it allows him to do that. But it also does another cool thing, is it actually acts as a way of detecting whether there's a leak or not in that underground storage tank. And kind of the way that works, again, there's a pretty sophisticated software program that's programmed in these automatic tank gauges, and what the probe will do and what the ATG will do, it'll kind of reconcile with how much fuel is sold. So say in that one day, the station sold 850 gallons. Well, through the probe and the float, it knows how much fuel was pulled out of the tank. So at the end of the day, if 900 gallons were pulled out of the tank, it sends an alarm and says, hold on, wait a second. If we only sold 850 gallons and we pulled out 900 gallons, what happened to that other 50 gallons? You know, maybe something needs to be inspected and see if there's a leak somewhere in that tank or somewhere in that system. So our automatic tank gauges act as a way to look at the level of fuel, and also acts as a way of detecting if there's any leaks in that underground storage tank. So moving down, you'll see the next opening, another probe coming down from grade or coming from surface, and you see this one kind of stops right at the top of our tank, and what that will be is a interstitial sensor, or a probe that goes down and monitors that space in our interstitial tank. Again, another way of determining whether that tank may or may not have a leak in it. We want to monitor that space, and that's what that opening there is. And usually at surface, what those will be is anywhere from like a 12-inch or an 18-inch manhole cover will actually, encase the tops of those probes or the top of those sensors at the forecourt or at our tank pads.
So we thought we'd bring out to an actual site and see what those components look like when they're on the tank pad. So I'm actually standing on a tank pad right now. You can actually see the series of manhole covers in a row, and what that does is it actually, by looking at that, you can tell exactly where that tank is laid out. So right here I have 4 tanks laid out in this direction. Down through here, and then the last one through there. And one of the easiest ways to tell what type of product is in each tank is by the spill container color. There's an API code, American Petroleum Institute, that actually designates specific colors for the specific type of product that's in the tank. So the tank that I'm standing on right here, you see this is our spill bucket cover, is painted red. So that's telling me that this tank actually has premium fuel in it. The next tank down here, the spill bucket cover is yellow. So that tells me that there's diesel product in here. And then the next 2 tanks, the spill bucket covers are colored white. So that's telling me that's the regular or the standard unleaded product. So here they actually have 2 tanks with unleaded fuel that are probably manifolded together. Obviously they sell more unleaded fuel than the others, so many times they'll put 2 tanks in to meet the demand of the higher volumes with that type of product. So the manhole covers that we see here, this first one here probably is some type of monitoring probe underneath there. The next cover here is our spill bucket, which we talked about on the whiteboard. This is where they actually add the product. The cover usually right next to the spill container, this would be where my stage 1 vapor recovery adapter is underneath here. Now, what I want to point out is typically at most stations, this would also be color-coded as well. The API color code for the stage 1 vapor recovery would normally be orange. So many stations you'll see these covers actually painted orange. In this case, by looking at this cover, I can tell that it's just a standard manhole over that adapter.
I want to point out one other thing. It's not actually an opening in our tank, but if you look over here to the outside of our tank, this is what's known as a monitoring well. Really what it is, it's just a 4-inch slotted PVC pipe that goes down into the backfill that kind of surrounds our tank pad area. And what that does, it allows us to monitor kind of the soil or the backfill conditions outside the tank. You know, sometimes there'll be sensors down in there, and if that sensor detects any type of hydrocarbon or any type of gasoline, again, sends a sensor, and we know that there's fuel leaking into the area around the tank, and someone needs to, shut some things down and start inspecting and taking a look. So the way that you can see these at the tank pad, these manholes tend to be a little bit different. They're kind of specialized. They're usually bolted down. They're white. They have a black triangle. And it's kind of a way to symbolize, okay, this is a monitoring well. Don't open this thing up and try and put gasoline down into it. It's not attached to the tank. So just a way of kind of preventing fuel from accidentally being dropped down that monitoring well. But that's what that other thing you see coming down from our tank pad down into our underground storage tank environment. So that kind of wraps up the first module of our Retail 101 video, which is basically all the underground storage tanks and the storage tank components and valves and fittings. So stay tuned for part 2, where we'll go into how we actually move the fuel from the tank to your vehicle.